Hi, I'm Andy Trudick, Technology Editor for Electronic Design. Joining me today is Dima Mirnikov of Renesas to talk about a new product line in their AnalogPAK family. So, Dima, go ahead.
Yeah, my name is Dima Murakov. I'm Senior Director of Product Marketing. I am part of Analog and Connectivity at Renesas Electronics Corporation. And today I want to introduce you a new AnalogPAK parts. This parts a subfamily of a well-known GreenPAK programmable mixed signal matrix ICs. So there are two devices. One is SLG47011 and another one SLG47001 and that's a programmable mixed signal ICs with analog features. And before we start talking about this new ICs, I want to first highlight about GreenPAK and do that in a simple words, only going through 3 slides. So GreenPAK was started about 15 years ago, and the idea was to replace some popular mixed signal standard products and standalone discrete components. And we are doing that through the GUI-based GreenPAK Designer software, and I will show it today how we can do that. It's very simple and user-friendly process. We also use GreenPAK to provide reliable hardware supervisory functions for devices such as SoCs and microcontrollers. And finally, you always start as the first 2 steps, but there are some additional blocks you have available in GreenPAK. There are some more configurability compared to the standalone discrete circuit. Many engineers love create their unique functions using our chip, and they tailor it to their individual application requirements. And I also can show you how to do that. And the process is very simple, and there is a wide variety of devices from first one on the left, smallest one, 8-pin, 1.2 square millimeter device. Then we have a bigger device with more resources, and the biggest one is 4x4, 32-pin device. And today we're introducing 2 more devices, one in different package variants, 16-pin, 20-pin, and 24-pin. And I want just straightly jump to software and show you how you can use this part. So to do that, there is this called GreenPAK or Go Configure Software Hub. And this software have all our GreenPAK devices, including our newer devices. All devices have different power supply range, temperature range. Some of them have supported up to 125, different number of GPIO. Some of them are automotive qualified. Some of them have special features like state machines, and a newer part that we're going to introduce today have ADC, like this device, and DAC, and so on. And there are different differentiators, so you can select part based on your particular need. So as an example, I will take one of like a medium complexity device, and it's a SLG47001. And this is software look like. So on the right-hand side, we have different components available for the particular device. So different devices have a different set of components. This is main workspace. And to make a design, it's very simple. You just click on the component, and component will show up on a workspace. You can use it and move it around. We can zoom in. And for example, I can just go and connect this component to the pin. And you can see software automatically help me recognize that this pin should be used as an input, because this block is as input and connected right there. So we will connect to other pins. We will use another pin as an output right there, and another one here. Then double click on the block itself, and we will have a properties on the left-hand side. And I can configure this block as, let's say, OR gate, right? Or I can configure it custom truth table, but let's just use as OR gate and press apply. So See, right now we just created one OR gate function. That's the simplest function I think you can build using GreenPAK. Of course, you can start customization, or let's say I want to add AND gate, right? And you can put, after OR gate, I want to have an AND gate. I can connect internally the signal and use another pin as a signal. You can flip pins around and connect it. And here we start building sort of custom functions, right? We have OR gate with the AND gate, and we can continue to adding more functionality. So, for example, in this device, we have analog comparators. So I can click here, analog comparator will show up on a screen. You can see these analog comparators are dark gray. So currently they are in the power off state. So to turn on them, we need to connect this power up signal to the high level. And in my example, I will use VDD, just make them always on, and they become light gray. I will do the same for another one. So let's say I want to make a window comparator that monitor voltage on one pin, let's say between 3.0 and 3.6 volt, which is like a practical use case. So first of all, I want to use just one pin to monitor. I will select one of analog comparator and select same input source as comparator 0, press apply. So right now I'm monitoring the same input pin. And then I can go and select internal voltage reference to detect 3 volts. You can see there is internal reference from 32 millivolts up to 2 volts. If not enough, I can select, let's say, 1 volt and put input voltage gain divider in front of the positive input of analog comparator. So in my case, I will use divided by 3. And that will have a 3.0 volt detector right there. You have some other options, like you can select hysteresis if wanted. I will not do that in my case. And press apply. So right now the comparator 1 will monitor for 3.0 volts on pin 20. I can do the same for comparator number 0. I will select 1.2 volt reference and divide it by 3. That's about 3.6 volt voltage detector on pin 20. And then say, okay, I want to make a window comparator. That's why I need to put a logic gate. So I will enable logic gate here and put it right there, connect it to analog comparators, double click and implement and configure this logic gate as XOR gate and press apply. So right now, this is a window comparator looking on a pin 20 for the customized threshold. In our case, it's 3.0 and 3.6. And that's maybe not enough. I want still to customize even more. And I want to add a filter. So let's say I'm inside the window for some duration time and we can decide what we want. We can, let's say, use maybe 5 millisecond or 10 millisecond. So to do that, we have this multifunction components. This multifunction components can be used as some lookup table, diff flip-flop latch, or some counter delay like timing type of functions. I can select this counter delay in this case. The window should pop up here if you really want to change this. I will say yes, of course. And then this counter delay have multiple options as well. You can have a delay mode, which is like a filter mode, one shot, generate a pulse, frequency detector, which is like watchdog type of function, reset counter, more like a frequency divider, and so on. In our case, we want to make a filter function, so we'll use the delay mode, and then we can decide it what type of delay I want. Do I want to delay both edges, or rising edge only, or falling edge? Let's say I want to do only rising edge mode. And then how much I want to delay. So right now it's like 1 microsecond, but we talk about 10 millisecond, let's say. This is 8-bit counter. You can see counter can be up to 255. I put 255. It's still not enough. It's only 125 microsecond. However, we have multiple oscillators inside this chip. So I can go and select another oscillator or different divider for the oscillator. So if I select oscillator 1 divided by 264, it's still less than 10 milliseconds. So I can use oscillator 1 divided by 512, and then reduce this to 50, but too much. I can just tune it to make it 10 milliseconds and press apply, and that's become my filter for 10 millisecond for rising edge only, and just connect it, this lookup table, to this filter, and my filtered signal on output, I can just go and connect it to pin 18. We have flexibility to adjust this for duration, edge, reference. We can adjust logic, as you can see here. It's pretty simple and easy to use. So we almost finished our design.
If I may ask a quick question.
Sure.
So when I'm looking at this schematic a week after I've drawn it, how do I know that the input channel has been scaled by a factor of 3? There's nothing on the schematic.
Yeah, so you need to go to settings, like here, and you will see information of the threshold. Another way, what you can do is you can put a label here, right? And I can put 3.6 volt. So just put some comments for yourself what you're doing here. Because sometimes you can make this as a custom logic, right? You can also, let's say 0, 1. I can only like put 1 here, right? And it become custom logic. You can always put some comments to help yourself to understand what's there.
Yeah, I was just thinking in terms of the comparator scaling. It's not shown anywhere as far as documentation goes. You have to manually put it in.
Yeah, you need to find it in the settings of the chip of the block, and we can put here like a filter for 10 millisecond because it doesn't also show as well. That's right. So another point that here, for example, you see there are some pins blue, some pins are this orange golden color, so they power from different power supplies. What I can do, so I can use different power supply. I can, let's say my blue pin can be powered from 5 volt, my golden pins can be powered from, let's say, 3.3 volt, right? So just connecting, can make this as an output, just connecting this pin to this pin, make a level shifter from 5 volt in this case to 3.3 volt. Like that. So just connecting one pin to another pin, it make a level shifter, and that's in addition, can you also use the same pin for the AND gate here, for example. There's another block here you can see, which we don't use yet, this I2C block. So we have a special I2C word address where you write and data where will show up on this I2C outputs. So by connecting this pin to this pin, so this output to this pin, and let's make another one, we can make I2C IO expander. So let's connect few of them. Okay, so how many I did already? 4, 5, let's do it. So right now I made a I2C IO expander for 5 pins. All right. So you can see what we did. We made a sort of custom logic functions right there. Then we implemented a window comparator with a programmable threshold and filter, programmable filter for 10 millisecond. We made one level shifter from pin 2 to pin 19. And also we made an I2C IO expander for 5 lines. Everything in one chip. From resources point of view, you can see how much resources we have used. So about probably 20% of all resources or even less. So in reality, you can make way more complicated designs. Like I can generate a pulse. Let's say if I inside this window for 10 millisecond, I generate reset pulse to start the system, for example. And you can continue growing the design and add more functionality. Another point is that once I finish design, actually, I can even do a prototype using our tools. So you can go to debug mode. We'll ignore that. And we can select different platforms. So I can go and program samples using development board I have here, or we can go and do software simulation. So typically we suggest to do software simulation because it allows you to probe some signals inside the chip. So I will select OK. And then I will have a schematic library here. And what I can do is I can add a voltage source right there and put ground here and connect this voltage source to this pin 20 for our simulation purposes, right? And then let's say I want to simulate this window comparator function. I can put probes everywhere in the whole pass lane together with even with the oscillator. So once I do that, I can go to the settings for this signal generators and adjust them accordingly. So we'll use 5 volt for power supply. And then I will create my trapezoidal signal for the input. So I will use probably 5 volt. I make maybe 5 millisecond low. And I will make a very long rising edge, let's say 500. And then short high and short falling. And after that, I can adjust time, how much I want to simulate. So we have very long duration. Maybe I can make 600 millisecond ending time. After that, I can do start and ignore that and see if it works or not. It actually works well. So you can see first 2 lines is just a power supply. This is a VDD1. This is a VDD IO. And then we have this input that we draw. It's like 500 millisecond ramp from 0 volts to 5 volts here. And then we have 2 analog comparators, this green line and blue line. So blue, you can see go low to high whenever red is 3 volts. Green is whenever red is close to 3.6. And then we have this logic block that saying inside the window and generates this high level when between 3 volts and 3.6 volts. And then we have this counter delay one block, which is used as a filter and delays this edge, rising edge for 10 milliseconds, right? On the other hand, you can see it completely filters this pulse, this purple pulse on output. We don't see that because this duration is less than the duration of the filter time. So once you finish the design, what you can do is you can change platform and go to the development board. And this time I use device with a multi-time programmable NVM, and you can go and program sample right away. So I have a development board connected to my computer, and I press program button, and a few seconds later, we have NVM programming succeed, and we can take this sample from this development board and put it in my board for prototyping purposes. So that's how it's simple.
Yeah, I noticed you've got a onboard temperature sensor, just one, I guess.
Yeah, we have a temperature sensor which you can use to monitor the internal temperature of the die. You can feed this signal to our analog comparator and either do some actions based on a particular temperature level.
Is there a sleep mode for the chip to where you can sort of measure the ambient temperature, or no?
No, that's a die temperature or junction temperature. But actually, our heat dissipation is extremely low. So that's why ambient is typically very close to the junction unless you're loading this output pins significantly. Because let's say if you don't use any analog resources like comparators and oscillator, current consumption is below 1 microamp. Then depending on oscillator you are using, we have 3 different oscillators. The lowest frequency oscillator is 2 kilohertz, consume only 300 nanoamp current consumption. We have 2 types of comparators. One is low power comparator. This consume like a 1 microamp to 3 microamp current consumption. This higher speed consume about 50 microamp if I remember correctly. So the current consumption of the chip is extremely low. So unless you load it like driving LEDs, the junction temperature is very close to ambient.
Maybe you could talk a little bit about the characteristics of the comparator in terms of bandwidth and offset.
Yeah, so the part is actually, it's not super, this particular part is not really extraordinary. Everything is sort of quite generic. So the speed, for example, for logic is only like up to 50 megahertz max. Comparators like this one is about 1 megahertz max, and for low current consumption, like a 10 kilohertz speed. A reference is trimmed and quite stable, less than 1% over temperature, but it's not like a high performance comparator. The idea is actually to integrate all the standard simple components that you have in almost all applications, right? So very often, very often you have many different standard components. You have some gates, you have comparators, and you need to replace them. And you can integrate them in one chip and significantly get a lower cost solution.
Okay, that makes sense. And then all of the available resources on this particular device are listed in that checklist on the right.
Correct, yeah. And you have different devices. So we have like 50 different part numbers with different resources and package sizes and performance characteristics. So if you're saying, oh, I just use 20% of the resources, maybe you need to use a cheaper device, right? And all of them are far below $1. So all of them are extremely cost effective.
So as I'm doing a design, I run out of resources. Can I take the schematic and everything and just pull in a larger device, or do I need to start over again?
Yeah, so unfortunately, all devices have some sort of unique resources very often. Like comparator, maybe speed is not the same, right? Or maybe reference range is not the same. So you need to switch from one design, like you need to manually move from one design from one chip to another chip. Or you can request our team to support you or help you. Let me go back to the PowerPoint if no questions. So considering this ability to integrate multiple components, we have been very successful and continuously growing this family and growing our volume. So we have shipped over 5 billion units for GreenPAK and GreenPHAT ICs together and continue growing. I think that's saying that we have been successful and have been successful in many different areas like IoT consumer, as well as infrastructure like servers, as well as industrial automation and factory automation application. And currently we start gaining also shares at automotive application, because you have some standard components almost in all the solutions, right? You almost always need power sequencing if your system is sort of complicated, right? You always need reset function. You always have some discrete IO expander or comparators, and that's why these parts become extremely popular. So GreenPAK is focusing more as a power management. So there are some load switches integrated, and we have devices with integrated LDOs, while GreenPAK is just a standard components like comparators, logic, D flip-flops, timers, and right now we're adding amplifiers and ADCs. All right, so as a benefit, what I want to highlight is the following. So you saw how we replace multiple components, right? So imagine you have a standard OR gate, AND gate, IO expander, and right now you can just go and put this in one IC. And what you can do is you can integrate all this function in one small GreenPAK device, and at the end have a significantly benefit from cost point of view. You can also have a fewer components and have less routing and smaller PCB footprint. But also another thing that I want to mention is differentiation. So when you take a standard comparator, right, and logic gate, maybe you cannot do, like, you want to make some customized reset function used to put the standard components, but you're limited to the standard components. Here you have this ability to create some own solution, right, with all these components. You have more customization. So an engineer loves this. They want to differentiate. They want to innovate. They feel like they are ASIC designers by putting all these components. So that's one of the greatest benefit of GreenPAK. You saw that we have this ability to turn on analog comparators, right? So all the power-hungry components, and even it's like less than 1 microgram, it's considered to be power 100 for us. All of them can be dynamically turned on, turn off. We can go to current consumption like below 100 nanoamp, actually looking for the input signals to react and start something, right? So you can have, oh, I want this analog comparators only on when this OR gate active. So OR gate is just doesn't consume any current in our case. And then wake up and do some actions. Adapt design is needed, right? So it's so simple. We can go back to our design and adjust timing, for example. Oh, I want not 10 millisecond, I want 5 millisecond, right? Just tune it and press apply, and that's your new design, right? Or instead of and I made a mistake, I want to have an end, right? Just go and change it and press apply, and that's your new design. And you can go and program a new sample again. And fast time to market, so our lead time is 8 weeks. So the process development is simple, production lead time is short. And finally, even it's a programmable solution, you have ability to log the design. So we have a security mode where you can log the design for being read or write or read and write together. So at the end, it become a custom function, like a black box with a custom function. Nobody can read it back. Nobody can copy it. It's also cost-effective and low power consumption. And so the steps, I think we just go a little bit through that, right? So you select a part, you make the design, you can simulate and then program the design, and you get a custom IC with tailored to your application function. And you saw that it just took us a few minutes to make the design. And for prototyping, we have this development board that allow you to apply external signals and prototype in your system. No NRE, no production commitment until customer plays the PO. As I mentioned, 8-week production lead time, and we often generate a custom datasheet tailored to the particular application. So we take the design and use the design to generate a custom datasheet.
So when you're doing this prototyping phase, you're doing it on that board, and you can program the individual devices. Now, when you say 8-week production lead time, is that like a custom masked device?
Correct. It's not really a custom mask. So it's a custom program. So we're stocking materials, waiting for PO, right? And the same device can be used as a system reset, as LED blinking or LED driving, as power sequencing, as some protection circuits. So we know it's like a generic device. It's not really custom for a particular customer, right? It's just waiting for being programmed for a particular customer. So we stock these devices, right? Once we get a PO, we just took these devices and program them, mark and tape and reel, and ship to customer, right? And then we backfill our materials.
Okay, so you're doing the programming at the factory once the configuration has been
Correct.
determined by engineering.
Yes.
So subsequently, can the device be reprogrammed in the field?
So it's a good question. So it depends on device. So there are devices that have integrated multi-time programmable NVM, and they support in-system programmability. And there are only 3 of them right now, and we continue to grow them, this set of devices. But most of the devices have integrated one-time programmable NVM. So it means you cannot upgrade it in the field. One-time programmable devices are very cost-effective because that's memory is extremely small and tiny. But yeah, it doesn't provide this flexibility. On another hand, many cases where a device is used, like a power sequencing or system reset, my experience, nobody wants to touch the designs once in the field. That's reality.
So you have me curious on the one-time NVM. Is that literally a prom again? Are we blowing fuses these days, or how's it work?
Yeah, so it's a floating gate NVM that extremely compact and very reliable, and we configure this, and yeah, we configure this program, this NVM by charge injection. And then once chip wake up, we actually reach that NVM back and configure all the blocks.
So what kind of quals have you done on the memory and on the device in terms of automotive space, blah, blah, blah?
Oh yeah, that's a lot of qual done, and this memory is extremely popular, ships in the huge volumes, very reliable, and we continuously doing quals and we pass all the needed qual. So memory never been an issue actually.
And then temperature range, is that sorted or binned, or does it function over a wide temperature range? What's the story on that part?
Yeah, so it's again, there's so many devices, and some devices support from -40 plus to 85. Some devices that support from -40 to 105. And there are automotive devices, grade 1, grade 2. So that support up to 125. So you can actually, I think if you go to our software, you can, I believe you can filter out by temperature range here, right? So there are only few devices, on all of them are automotive grade 1 that support, except one, support up to 125, and then few devices that support 105. Okay, so we will go and talk about new device that we are going to introduce, and the star for today is actually this device, AnalogPAK SLG47011. So AnalogPAK is a subfamily of a bigger GreenPAK family, and this AnalogPAK have just more high-performance analog features, and that's the differentiator. And for us, it's one of the biggest step forward. So we have added multiple new blocks, such as programmable gain amplifier. We have added 14-bit SAR ADC, DAC. We keep analog comparator. And what we can do is we can use this device to extend performance of low-cost MCU. So very often saying, oh, I need higher performance ADC together with programmable gain amplifier. Potentially, you can find MCU that have this ADCs or such type of ADC, but very often this MCU is already overkill for you, right? And you can have way more other blocks together with this battery ADC. So what you can you can just use low-cost MCU and use our part to improve performance of your analog. Another way you can offload MCU, right, and move this like analog to digital and digital to analog conversion to our chip. You can also use our chip to replace some complex analog front end. Sometimes it's with MCU, sometimes it's without MCU as a standalone AFE that you can read data from using external MCU. So this device is a smaller size and very low cost, considering it's one of the richest analog and digital resources part. And as always, we care about energy efficiency and energy saving. So all the blocks have ability to dynamically turn on to off. All right. So from key functions supported, I will not go through all of them. Just want to highlight it here. First of all, measurement. There are multiple ways you can measure data. We have integrated analog digital converter. You have ability to amplify the signal. You can select between single-ended differential. For data processing, you have also multiple options. There's a hardware mask core, which allow you to do multiplication, adding, shifting. You can do averaging. You can implement oversampling, and all this is hardware blocks. From logic control, you have this GreenPAK as a state asynchronous state type of machine D blocks, like I showed before to you. And from output, there is ability to get analog outputs through the 12-bit DAC, PWM, and there are I2C and SPI interfaces. From application, fields of application, so we don't really want to limit customers and all our users to particular applications. Here we just list different examples, such as like current power monitors, where you can use ADC and programmable gain amplifier to sense the voltage drop on a shunt resistor and calculate power using our mask block. You can have a capacitor sensor button also implemented with a baseline tracking for compensating temperature change. protection, voltage, current, power, temperature protections. You can use this device as AFE. You can have a use case where we're going to use this device as a hard modem for industrial automation customer, for example. So you don't really limit for this. So you have just these blocks, and as long as you can understand these blocks and functionality, you can create your use case, and we allow the customer so smart, and all the engineers in the world are so good, so they just create and find in different use cases for this type of devices. Here is a block diagram. So for this device, what I want to highlight here is that we actually came from startup that was acquired, and right now eventually we landed in Renesas, and Renesas is a big family, so we benefit from being a part of a big family. We leverage IPs from different groups of Renesas. For example, for programmable gain amplifier, we leverage op-amps that have been designed for many years in Renesas, one of the companies that have been acquired. Same for ADC, same for DAC. Like the same DAC is used in one of the Renesas MCUs. So why spend many years to optimize them? We just grab all these IPs from many different groups of Renesas big family, and then put it in this cool programmable platform, add some digital block around, and that's how we get to this particular device. As you can see here, we highlighted some new blocks like programmable gain amplifier with the input max and ADC, and digital buffers for averaging, storing, and oversampling. Then we have mask core, we have DAC, we have memory block which you can use to store some data. Bits converter, we have 2 oscillators, we have 2 options for serial communication, and one of the highest number of logic blocks, especially timing blocks, we have in the whole GreenPAK family. And everything fitted in this small 16-pin 2x2 millimeter 0.4 millimeter pitch package, QFN package. And this time we benefit from advanced process, which puts some restriction on the power supply. So we're getting a power supply from 1.71 to 3.6 volts.
What kind of sample rates can the converters support?
It depends on the resolution. At lowest, like 8-bit, you can go, if I remember correctly, to 2 megasample per second. All right.
And then the number of LUTs varies per device, or is it fixed in this particular
Correct.
device?
Yeah, it's varied for per device. So in this particular device, we have, for example, have the highest number of this counter delay blocks that can be used for filtering, for power sequencing, or maybe wait before doing something. So from LUTs, there are some parts that have more LUTs. So another one is also part of AnalogPAK. It's SLG47001 and SLG47003. So actually, it's the same device, it's just used in 2 different packages. So first one in 20-pin, and 47003 is in a 24-pin package, which have additional 4 IOs. So we have already devices we have one device with the integrated operation amplifiers. But this time we again leveraging IP that have been developed for 10 plus years in Renesas. It's a ultra low offset op-amps, and we put 2 of them. So we have older devices and just go and replace this general purpose op-amp with this precision, high performance, optimized op-amp. We have integrated 2 10-bit digital restarts, so you can have ability to do some tuning, like you can adjust gain, for example, or use this restart as adjusting a cutoff frequency. We, instead of having many comparators, we just introduced a comparator with multi-channel sampling, allow you to sample up to 6 different channels. So it can be 6 different pins, or it can be used one like same pin with multiple thresholds. So you can amplify the signal and then connect this amplified signal to the comparator and feed it back to wake up MCU, for example. We keep our this LUTs, counters, and so on, this GreenPAK configurable logic. as always, all blocks can be powered on depending on the need. And we have a CRC check. That's what we are doing for all our newer devices. Fields of application, this part have I think a little bit more focus. It's focus more on analog front-end type of applications. So for example, analog front-end for gas sensor or for diodes or for like photodiodes. Or you can use this as a low power programmable gain amplifier where you use rheostats to adjust gain. And low offset op-amp allow you to used in the shunt current sensor applications. And we believe there are many other use cases for this device with the focus on whenever op-amp is used. Because if op-amp is not needed, you just can use another GreenPAK, which will be lower cost. From resources point of view, it's more like a general purpose GreenPAK. We just used a very common resources, optimize their quantity to balance from cost point of view. So one of the key aspects for this particular device is focusing on cost optimization. But what we're doing also, we keep this analog capabilities like this 2 10-bit digital rheostat, single analog switch, 2 op-amp, and this multi-sampling analog comparator. And as I mentioned before, 2 package options.
So on the op-amp, is that really just a PGA? In other words, do I have access to a network of passives where I can configure the op-amp as a low pass filter, for instance, or something else?
So actually, it's not really even PGA. So in the previous part, it was a PGA, but this is just as, like you can say, a standalone op-amp, right? So you have access to all the terminals. You have access to positive, negative input as well as output. So you can put external resistors to set feedback, for example, for amplification or and together with our rheostat. So it's just a, you can say, general purpose op-amp, but with quite a low offset and 400 kilohertz bandwidth.
Okay, and then the path through the switches is to the internal rheostat, and to the reference, there's no path through switches to the actual I/O pins. Is that right?
No, sorry, maybe this is a little bit confusing. So this box is an I/O. So you have access to so there is a dedicated pin that op-amp connected to.
So there's no variable resistive device from device to device in terms of dealing with manufacturing yields, et cetera, if you were to implement, let's say, a low pass filter for an AFE or something.
No, so yeah, typically you need to put some passives outside because just rheostat itself will not be enough to implement your cutoff, your low pass filter, for example. So you will need to put capacitor outside, right, and use our rheostat in the feedback loop. Op-amp is quite good performance, and you can see it here. It's a rail-to-rail input, rail-to-rail output, and very low offset and low offset drift with temperature. So I think that's the last slide, just to compare what we have right now. So this SLG47004 is a device that currently available in production for a few years and gain some success so far. And this is a new device that we are introducing today. So before we have 3 general purpose op-amps that can be used also in the instrumentation amplifier mode and different bandwidth option, which also allow you to adjust current consumption accordingly. This time we use 2 zero drift, ultra low offset, low current consumption op-amps with a single bandwidth, but very well optimized from size point of view. We are still having 2 digital rheostats, but what we did, we just optimized size for this rheostats internally by using special techniques. We, instead of having 2 separate analog comparators, we have 1 analog comparator with the 6 channels together with the analog max in front of it. We reduce number of buffers as well as reduce number of this logic macro cell, like number of lookup tables and timers. We have introduced this pattern generator here, which allow you to generate up to 59 bit width pattern And this time we also used cost-optimized one-time programmable NVM instead of previously we used multi-time programmable NVM. There's a new device available in 2 package options, and we have managed to significantly reduce cost for the device about 1/3.
Sounds good. So in terms of collateral, you've got eval boards available for these new devices, or is that still in the works?
Yeah, we do. Of course, yes. We have all the needed development boards. So it's actually the same development board is used for all GreenPAK devices. You just need to have a different socket adapter and also deep adapter. So same development board as used for all GreenPAKs, just different adapters which are available at distributors, as well as we will have some special evaluation boards for the higher performance part, which also already available.
And then in terms of tools, do they run locally on my machine? Do they run on your machine in the cloud? Where does that go?
Yeah, so you need to use this software. It's called Go Configure Software Hub. It's available for free for download at renesas.com webpage. It supports Windows, Linux, and macOS. It will be installed locally on your machine. Together, simulation also is done locally on your machine.
So do we need to have the board or a device in hand in order to run simulations of a...
No. So simulation is just an ngSpice simulation model, which is integrated inside the software. You don't need to use our development board to run the simulation. But if you want to program samples or do hardware prototyping, yes, of course, you need to have a development board together with the sample.
And in terms, you just said ngSpice, so can you actually export the Spice code to run into something else?
No, currently you can import some models to our software, but we don't support exporting yet.
All right. I appreciate your time. Thank you.